Yes, this is a 5,000 horsepower, 13.8 kV combination motor starter for use with a synchronous motor that contains a brushless exciter. It's a complete combination starter with inline bypass contactors, disconnect, fusing, as well as a solid-state power section. This is the disconnect section of the starter, and we've got the disconnect open up. And you can see that the disconnect switch is in the on position and it's closed. The disconnect switch in here is a fully rated load break disconnect, power entry into the bottom, and then power exit out of the top. The disconnect section also contains the E-rated fuses to provide for short circuit protection for the motor as well as the starter. In the top section of the disconnect section is also surge arresters, which provides for up to 60 kV of BIL protection for the system. Next to the disconnect section is the input filter section of the starter. We come out of the top of the disconnect section here, come down through the CTs. There are 2 CTs per phase. In the system, 1 CT feeds the multi-lin for motor protection. The other CT feeds the solid-state starter section for current regulation. We come down here through the insulated bus to the input reactor, and from out of the input reactor to the output reactor, and from the output reactor we come along here to the inline bypass, the inline vacuum contactor. In the middle of the inductors is an RC filter, and the combination of the input reactor, output reactor, resistor, and capacitor form a filter section that provides the VDT as well as the IDT protection for the solid state section. Whenever the starter is fully operational and the bypass contactor picks up, which is taking off at this point of the bus and comes along here to the input of the bypass vacuum contactor, it provides for a run bus circuit during normal operation. It effectively bypasses the filter section, and yet the filter section is still actively in the circuit, providing additional transient protection for the equipment. Okay, from the filter section, we then pick up power for the input to the stack through the contactor section. As we said earlier, this is the input power connection along here to the inline vacuum contactor, and from the output of the vacuum contactor we go to the input section of the solid state AC switch. Up here is the bypass contactor, which basically connects the run bus into the motor T leads after we're up to full voltage. Up in this section over here we go to the output section of the solid state starter, so therefore this becomes the motor T lead connection. This essentially becomes the power L connection to the input of the solid state stack. And we pick off of a section of the incoming bus right here and go through fuses to a resistor divider card to ground. The purpose of this resistor divider card is to provide for a low voltage feedback signal that is used to determine the magnitude of the incoming 3-phase 13.8 kV voltage into the system, and also provides for phase sequence protection if desired, and also provides for the phasing information as to when we can operate and fire SCRs. Then we can pick off of the output side or the load side of the fuses and come down here to the PTs. The PTs in the system are used with the multi-lin to provide for phase voltage protection, low line, high line, voltage imbalance, and for metering purposes within the multi-lin. Next to the contactor section is the starter solid state section. There is a separate low voltage section within the starter enclosure section that houses the microprocessor electronics, which provides for the heart of the operation of the system in terms of logic sequence, protection, determination of when to actually gate SCRs on and off, and the control of both the inline and the bypass contactors. In this section over here we have a test and a run switch, which allows for the operation of the starter in test mode by bringing in an external 120 volts power to the test plug here. And in this operation mode you can provide for low voltage testing to prove that the microprocessor electronics as well as the contactors are operational. You can also verify SCR gate pulses within the solid state stacks, which are behind this door here in the starter enclosure section. This board over here provides the barrier between the high voltage and the low voltage from the resistor divider card, as well as from the CTs within the input section to the assembly. The purpose of this board is to provide a barrier so that we can clamp any transient voltages to a lower magnitude before they enter into the microprocessor section here. The microprocessor section then consists of a CPU board as well as a power board. The CPU board is the heart of the system that contains the microprocessor code. It determines the programming sequence of events as to when to actually pick up an inline contactor, when to drop it out, when to fire the SCRs based on the settings from the display section of the low voltage section of the starter. It will then allow for current regulation from initial currents to maximum currents, and also the rate of rise in terms of the time from initial currents to maximum currents. Underneath of the CPU section of the power boards over here is the power card. The power card then receives low voltage 120 volt power, sets up 5 volt supplies, 15 volt supplies for the microprocessor as well as the operational amplifiers on the power board. Does all of the conditioning for the input voltage from the resistor divider card through the barrier card over here. It also looks at the current transformers from the input section and provides for the operation of the digital to analog and the analog to digital converters within the heart of the system. In the starter enclosure is the SCR heatsink assemblies. The SCR heatsink assemblies are housed in a fiberglass enclosure within the starter section here, which is the final section of the entire combination starter. In here are 6 AC switches that we call cells that are configured as back-to-back SCRs to provide for variable voltage output. Each cell is rated 6 kV, so there's a total of 36 kV of isolation or peak inverse voltage rating from the top of the starter section here to the bottom. The bottom section over here is where we bring input power, and then output power flows up through here to the output of the stacks, which then comes over to here and forms the T connections where the customer can bolt on his motor connections here. And there's bracing provided on the sidewall of the enclosures to provide for mechanical protection so that the wires don't move during operation from mechanical forces caused by the current within the conductors. Each AC cell in the system requires gate supply voltage. We have 6 distribution transformer assemblies in here that provide high voltage and corona-free power from the low voltage compartment over here through this transformer to each cell. So we have a supply in here for each cell that comes out of these high voltage isolation distribution transformers. And if you notice, there are 6 of these. There are 2 for each AC switch section in here, and each one of these then provides power for approximately 3 cells for a total of cells of 36 AC cells in the system. The cells are fiber optically controlled by these fiber optic connections here from the low voltage section. Thus we have light pulses that are actually used to trigger the SCRs on. This provides for a very high degree of isolation between the 13.8 kV line-to-line voltage within this side of the enclosure and the low voltage compartment over here. Spacings in the system are set up to meet CSA standards, which provide for 6 inches of space between line to line and close to 7 inches of line to ground spacing in here. This, in combination with the surge arresters we mentioned earlier, provides for BIL, which is basic impulse level protection for the system, and also provides enough clearance to provide for a long lifetime of use by assuring that we have partial discharge or corona-free operation. This is another view looking from the side to be able to see the actual AC switch cells within the assembly as viewed from the side. The reason these cells are turned on a front to back or a side mount is to provide for easy access from the bus connections coming into the unit and going out of the unit. There is enough space in here to allow for each cell to be extracted from a maintenance viewpoint for inspection or for testing from the built-in self-testing mode of the microprocessor control. This is the whole overview then of the starter. The application for the starter is to operate a 13.8 kV, 5,000 horsepower synchronous motor. The motor is manufactured by GE in Canada, and it is controlled by a separate field exciter package that determines when to actually apply the field to synchronize the motor. The system then is engineered to provide for coordination between the exciter package and the solid-state starter section. Testing of the unit was accomplished in May of 2000 to test the actual motor along with the starter and the exciter package and to simulate field conditions that the customer would encounter during actual operations.